Hello everyone, my name is Kelly Duan. Welcome to Audit Analytics. For this module, I'll talk about classification. Our objectives for this module is to understand the concept of classification, understand the different classifiers and how they work, how to evaluate the performance of different classification models. Then we will learn how to apply classifications to different audit procedures and what kind of tools you can use to perform classification. Machine learning includes three main types of paradigms. One is unsupervised learning. Usually, it deals with unlabeled data. This includes clustering, which divides the data into different groups based on the information found in the data that describes the objects and the relationships. The second one is dimensionality reduction. Especially in today's big data environment, data sets with many different features, hundreds or thousands of attributes, tend to have a high dimensionalities. As the dimensionality increases, the computational complexity increases. It gets harder to analyze the data to gain meaningful information. Therefore, reduced dimensionality is commonly performed to eliminate irrelevant features, reduce noise, identify the key features that could represent the whole dataset, make the model easier to understand. PCA, Principal Components Analysis, is a common technique to use. The next type is called reinforcement learning, which means the model learns from the data analysis to solve a problem, but the model is not trained with a labeled dataset. The model is like a decision-making agent. It receives feedback from a set of trials and errors, learns the best policy, and is more like a behavior learning model. Then the next type is supervised learning. Usually it deals with the labeled data, which includes classification, regression. Supervised learning is about there is an input and an output. The task is to learn the mapping from the input to the output, and the correct values are provided by a supervisor. We will discuss more about classification in this module. Classification is a type of a machine learning method. Specifically, it is a type of a supervised machine learning method. It is a task of assigning objects to one of several predefined categories. Some examples are detecting spam email, predict companies' future bankruptcy probability based on different financial factors, predict future defaults of customers based on different variables such as the history of past payment, the amount of a bill statement, the amount of previous payments, etc. In general, the input data for a classification task is a collection of records, and each record, also known as an instance or example. It can be characterized as a tuple x, y, where x is the attribute set and y is the class label, which is a special category or target attribute. Here, the x, which is the attribute set, can be discrete and can contain continuous features. In terms of a data type, discrete attributes has a finite or countably infinite set of values, can be categorical, such as a zip code or ID numbers, or numeric, such as counts. So it's often represented using integer variables. Continuous attribute is one of those values that are real numbers, such as a temperature, height, or weight. It's typically represented as floating point variables. The class label y must be a discrete attribute. This is a key characteristic that distinguishes classification from regression. Therefore, classification can be defined as the tasks of a learning classification model that maps each attribute set X to one of the predefined class label Y. Classification techniques are most suited for predicting or describing data sets with binary or nominal categories. Oftentimes, when we perform classification tasks, we need to convert the data type, such as from numeric to nominal. This graph here illustrates a general approach for solving classification problem. The framework involves a two-step process. The first one, an inductive step for constructing a classification model from the data. The second step is called a deductive step for applying the model to test examples. In general, we divide the dataset into training set and testing set. For example, 80% as training and 20% as testing. The training set consists of records whose class labels are known. It's used to build a classification model. Then subsequently, apply the classification model to the testing set, which consists of records with unknown class labels. A classification technique, or also called a classifier, is a systematic approach to build a classification model from an input dataset, such as decision tree classifiers, rule-based classifiers, or neural networks. So each classifier employs a learning algorithm to identify a model that best fits the relationship between the attribute sets and the class labels of the input data. So the model generated by learning algorithms should both fit the input data well and correctly predict the class labels in the testing set. So it's important to build models with a good generalization capability. There are different types of classification techniques. We will go over a few of them in this set of videos. The first one we will talk about is decision tree classifiers, which is a simple but widely used classification technique. To construct a decision tree, we can ask a series of carefully crafted questions about the attributes of the record. For example, here, you can ask some yes or no questions. Each time we answer a question, a follow-up question is asked until we reach a conclusion about the class label of the record. It follows a recursive fashion by partitioning the training records into successively pure subsets. Once a decision tree model has been constructed, classifying a testing record is straightforward, just to apply the decision tree classifier to the test dataset. It also follows the same logic as before. Starting from the root node, apply the testing condition to the record, meaning ask a question, then follow the appropriate branch based on the outcome of the test, until we find the class label of the record. So some questions will raise during the decision tree model construction. How should the training records be split? And when to stop? To split the training set, first, the algorithm must provide a method for specifying the test condition for different attribute types. Is it binary, nominal, ordinal, or continuous? We also need to know the ways of splitting the tree, whether it is two-way split or multi-way split. Then the next question is when to stop. There are two ways to tell. First one is to stop splitting if all the records belong to the same class or have identical attribute values. The second way is just stop early termination. So now the question is how to determine the best split point. As you can see from the example listed here, this dataset provides information about customers' gender, car types they drive, shirt size, and class. So in this case, we can construct a decision tree. The records are split into two classes, class 0 and class 1, and each class has 10 records. Then next, we need to decide which splitting way or test condition is best when we base on gender or car type or customer ID to build the decision tree. The measures developed for selecting the best splitting point are often based on the degree of impurity of the child nodes. The smaller the degree of impurity, the more skewed the class distribution is. For example, the first example here shown on the left, the two classes are divided equally. So in this case, it has the highest degree of impurity. The second example on the right, on the other hand, it has a low degree of impurity. The distribution of the classes is very skewed. As you can see that class 0 has 9 records, but class 1 only has 1 record. So normally, we use 3 different impurity measures, which are Gini index, entropy, and misclassification error. The first 2 are used more often. When we compare the impurity measures, the smaller, the better. For example, the Gini impurity shows that the data point we have randomly chosen for the splitting from the dataset, how it is incorrectly labeled. In our example here, the Gini index for the second example is smaller than the first example. Therefore, the second example is the better split to choose. This slide shows the calculation formula for each impurity measure. Let's see an example how they are calculated. In our previous example, we have a different splitting nodes. The example shown here is based on the card type. Before splitting the nodes, we have 10 instances for each class 0 and class 1. Then, for the first splitting nodes family cards, we have 1 instance for class 0 and 3 instances for class 1. Total, we have 4 under family cards. And for sports, we have 8 instances for class 0 and 0 instances for class 1. So under this node, we have 8 instances. And for luxury cars, we have 1 instance for class 0 and 7 instances for class 1. So in this case, we have 8 for this node. So let's see how the Gini index and the entropy and the misclassification errors are calculated. So for the first splitting point, which is based on the family, as we said, for class 0, we have 1 instance, and for class 1, we have 3. So in this case, total, we have 4 instances under this node. To calculate the Gini index, based on the formula, for the first class, which is class 0, we have 1 instance under this class and total 4. So it's 1 divided by 4 to the power of 2. And for class 1, we have 3 instances under this class and total 4. So based on the formula, we'll do 3 over 4 to the power of 2. Then the final value is 0.375. And for entropy, based on the formula, here, this section is for class 0. So in this case, similar to the Gini value, we have 1 instance for class 0, and the total number of instances under this node is 4. So it's based on the formula, we have negative 1 over 4, then times the log 2 for 1 over 4. So this is for class 0. And the second portion here, this is for class 1. Same logic, we have 3 instances for class 1 divided by the total instances here. So the final value for entropy is 0.811. For the misclassification error, it's based on the maximum of the distributions. So here, 1 over 4, which is for class 0, and 3 over 4, which is class 1, whichever is the maximum value, which is 3 over 4. Then based on the calculation, this knows the misclassification error is 0.25. And the same logic applied to the second node. Based on the sports, we have 8 for class 0, and we have 0 instances for class 1. So under this node, total we have 8 nodes. And for Gini value is 1 minus for class 0 because we have 8 instances under this class and total number of instances under this class. And for class 1, we have 0 over the total number, which is 8 to the power of 2. So the final value for this node is 0. Same logic for entropy. This section here is for class 0, and this section here is for class 1. And same logic apply to the classification arrow. So the logic for this node is the same. So here is a quick check about your understanding of the concept. So we have a polling question. Which node has the lower impurity? Is it node 1, which the class distribution between class 0 and class 1 is 1 and 5. For node 2, the class distribution is divided equally. So I give you a few minutes to think about this answer. And the answer is node 1. As we mentioned before, the smaller the degree of impurity, the more skewed the class distribution will be. So in this case, node 1 is clearly more skewed than node 2. Also, the Gini index is smaller for node 1, and the calculation is listed here. So for the total instance for node 1 is 6, and for class 0 is 1 over 6 to the power of 2. For class 1, there are 5 instances, so the calculation is 5 over 6 to the power of 2. Then the calculation is pretty straightforward. So to find the best splitting node, we can simply compare the impurity measure before and after splitting among different nodes. Then choose the attributes best condition that produce the highest gain. In other words, choose the one that provides the lowest impurity measure after splitting. Decision tree in general is easier and computationally inexpensive to construct. You can quickly construct models and classify a testing record. So decision tree, especially for smaller size trees, are relatively easy to interpret. The accuracy of the tree are also comparable to other classification techniques for many simple datasets. It's quite robust to noises. However, the tree could get complicated when you have more different attributes. So if you are dealing with a dataset with many attributes, we usually consider to perform a feature selection, identify the relevant attributes before construct a decision tree. Decision tree classifier is considered as an eager learner because they are designed to learn a model that maps the input attributes to the class label as soon as the training data becomes available. So that's all for this video. Thank you for watching. Hello everyone, this is Kelly. Welcome back. Let's continue our discussion about classification. We have learned that decision tree classifier is considered as an eager learner. As an opposite model, as indicated here, nearest neighbor classifier, we often call it KNN, is considered as a lazy learner. As the classifier delays the process of modeling the training data until it's needed to classify the test data. So in this case, a KNN classifier represents each example or instance as a data point in a D-dimensional space, where D is the number of attributes. Then, given a test example, we compute its proximity to the rest of the data points in the training set, using one of the proximity measures, which is to see the similarities and dissimilarities between 2 points. So the data point in the unknown record is based on the class labels of its neighbors. So in this case, the basic idea here is to choose the neighbors for the test record. So we compute the distance between the test record, for example, the duck, to the training records. Then the classification of the duck is based on the classification of its nearest neighbor. So when we classify an unknown record by using KNN, we need first to compute the distance to other training record, then to identify the K nearest neighbors when the neighbors have more than one label. So the data point is assigned to the majority class of its nearest neighbors. So to compute the distance between 2 points, commonly used methodology is to calculate the Euclidean distance. Simply can be interpreted as the straight line distance between 2 points. So using K and N, it's important to choose the right K. If K is too small, the classifier may be susceptible to overfitting because of noise in the training data. On the other hand, if K is too large, the classifier may misclassify the test instance because its list of nearest neighbors may include data points that are located far away from its neighborhood. Also, nearest neighbor might produce wrong predictions if the dataset was not properly pre-processed. This is mainly due to the scaling issue. For example, the height attribute has a low variability. The weight attribute and the income vary in a bigger range from 90 pounds to 300 pounds, or from $10,000 to 1 million. So the proximity measure may be dominated by differences in the weights of a person. So another issue with the nearest neighbor is the Euclidean distance measure that used to determine the similarity and dissimilarity between two instances. So the accuracy of the measure could be impacted if the data has high dimensionalities, and it may produce counterintuitive results. For instance, the example shown here, the distance between the left side points and the right side points is the same. Both of them are 1.4142, which means the two sets of data points are similar. However, as you can see, they are completely different. So one solution to this problem is to normalization, bring the data point to the same unit length. So to summarize some characteristics of KNN, first, KNN classifiers use specific training instances to make predictions without having to maintain a model derived from data. The algorithms require a proximity measure to determine the similarity or distance between the instances and a classification function. So we can get a predicted class of our test instance based on its proximity to other instances. As we mentioned before, it is a lazy learner as it doesn't require model building, but it can be expensive to classify unknown records because it needs to calculate the proximity values. So KNN classifiers can produce wrong predictions unless the appropriate proximity measure and data preprocessing steps are taken. If the attributes have low variability, the proximity measure may be dominated by certain value. It's important to consider the scale of the attributes. And the next topic we're going to discuss briefly is artificial neural network. The study of artificial neural network was inspired by attempts to simulate biological neural systems. Human brains contain about 100 billion interconnected neurons. Each neuron receives input signals, for example, the visual signal of a cat, from other connected neurons. If the combination of these signals exceeds a certain threshold or activation level, the neuron fires, that is, transmits an output signal to the other neurons. So humans, deep layers of neurons and their complex interconnections result in a thinking machine, the human brain. So neural networks are models of biological neural structures. A simple neural network architecture known as a perceptron. It consists of different types of nodes. Input nodes, also known as the input layer, which are used to represent the input attributes. An output node, which is also known as output layer, which is used to represent the model output. Everything else in the middle is known as the hidden layer. So the nodes are commonly known as neurons or units. The starting point of most neural networks is a model neuron, as a picture showing here. This neuron consists of multiple inputs and a single output. So each input node is connected via a weighted links in the hidden layer to the output node. The neuron will combine these weighted inputs and with reference to a threshold value and activation function. For example, the sign function, positive or negative, to determine its output. So this behavior follows closely our understanding of how real neurons work. So the network may contain several intermediary layers, which is also known as the hidden layers. We usually call this layer as the black box. Multi-layer artificial neural network just contains many different hidden layers as shown in this picture. The network may use different types of activation functions other than the sign function, such as a linear, sigmoid, which is the logistic function. These activation functions allow the hidden and output nodes to produce output values that are non-linear in their input parameters. These complexity allow multi-layer neural networks to model more complex relationships between the input and output variables. Now, I have a polling question here to test your understanding about neural network. Which of the neural network layers is also known as the black box? Is it input layer, hidden layer, or the output layer? The correct answer is the hidden layer. This is particularly predominant in the case of a multi-layer network because there are many different connections and nodes. To fully understand how it works could be challenging. So before we train a neural network to learn a classification tasks, we need to consider the following design issues. The number of nodes in the input layer should be determined. We can assign an input node to each numerical or binary input variable. The number of nodes in the output layers should be established. For example, for a two-class problem, it is sufficient to use a single output node. But for K-class problem, there will be K output nodes. The next one is to select a network topology. For example, the number of hidden layers and hidden nodes. The weights and the biases needs to be initialized, but random assignments are usually acceptable. Last but not least, training examples with missing values should be removed or replaced with the most likely values. So that's it for this video. Thank you for watching. Hello everyone, this is Kelly. Welcome back. Let's continue our discussion about classification. In this video, we'll talk about a new classification method called ensemble method. An ensemble method constructs a set of classifiers from training data and performs a classification by taking a vote on the predictions made by each classifier. The basic idea is to construct multiple classifiers from the original data and then aggregate their predictions when classifying unknown examples. So we can construct ensemble classifier in many different ways. We could by manipulating the training set. In this approach, multiple training sets can be created by resampling the original data according to some sampling distribution. The sampling distribution determines how likely it is that an example will be selected for training, and it may vary from one trial to another. Two examples of this approach is called bagging and boosting. We will discuss more in details in the next few slides. Another way is by manipulating the input features. A subset of input features is chosen to form each training set. The subset can be either chosen randomly or based on the recommendations from a domain expert. A common example is called random forests, which manipulate the input features and uses decision trees as its base classifier. So we can also manipulate the class labels. This method can be used when the number of classes is sufficiently large, and we can also use the way to manipulate the learning algorithm. Apply the algorithm several times on the same training data, and that may result in different models. For example, artificial neural network can produce different models by changing its network topology. So a classifier is usually trained to minimize its training error. The expected error of a classifier is affected by variability in the training data, because a different composition of the training set may lead to different decision boundaries. So bagging, which is also known as bootstrap aggregating, a technique that repeatedly samples data with replacement from a dataset according to a uniform probability distribution. Each bootstrap sample has the same size as the original data. Because the sampling is done with the replacement, some instances may appear several times in the same training set. For example, in the sample listed here, round 1 and 2 and 3 has the same size as the original data. And round 2 and 3, they both have 1 in their data. To illustrate how bagging method works, consider the data set shown here. X is a one-dimensional attribute. Y devote the class label. Suppose we apply a classifier that includes only one-level binary decision trees with a test condition x less or equal to k, where k is the best splitting point with minimal or smallest entropy. Without bagging, the best split point is at either x less or equal to 0.5 or at 0.75. Assume we apply the bagging procedure on the dataset using 10 bootstrap samples. So on the right, it shows the decision boundaries produced by the classifier. For example, in round 1, the best splitting point is 0.35. That means all the points on the left of 0.35 will be classified as a positive 1, and all the points on the right will be classified as negative 1. Another example, for round 4, the best splitting point is 0.3, which means all the points on the left of 0.3 will be classified as positive 1. On the right of 0.3, they are classified as negative 1. So in this case, in this example, we do the bagging method for 10 rounds. Then we classify the entire data set by taking the majority vote among the prediction made by each classifier. For example, at threshold 0.1, majority class is assigned as positive 1. Then the predicted class is positive 1. But at the 0.4, this point, majority class is assigned as a negative 1. So the predicted class is negative 1. Since every sample has an equal probability of being selected, bagging does not focus on any particular instance of the training data. It is therefore less susceptible to model overfitting when applied to noisy data. Boosting is an iterative procedure used to adaptively change the distribution of training examples so that classifiers will focus on examples that are hard to classify. So for boosting method, all records initially are assigned an equal weight to each training example and adaptively change the weight at the end of each round for those harder to classify records. Suppose, for example, in example 4, 4 is difficult to classify. The weight will be increased in the next iteration as it gets misclassified repeatedly. AdaBoost is commonly used for boosting method. So to recap what we have learned so far, a simple question is here. Which classifier method is using a uniform probability distribution? Is it bagging or boosting method? So the answer is bagging. As we discussed earlier, under bagging method, each sample has a uniform probability of being selected. Boosting is using an iterative procedures to adaptively change the distribution. The next classifier we will discuss is called random forest. Random forest is a class of ensemble methods specifically designed for decision tree classifiers. It combines the prediction made by multiple decision trees, where each tree is generated based on the values of an independent set of random vectors. So random vectors are generated from a fixed probability distribution. Bagging using decision trees is a special case of random forest. So the randomization helps to reduce the correlation among decision trees so that generalization error of the ensemble can be improved. An AdaBoost is a commonly used boosting method. AdaBoost classifiers depends on its error rate to generate a parameter called alpha to determine the importance of a classifier. So the algorithm used the parameter to update the weight of the training examples. So the weight is increased for those instances classified wrong and decreased weight for those classified correctly. So instead of using a majority voting scheme, the prediction made by each classifier is weighted according to the alpha parameter. This approach allows AdaBoost to penalize the models that have a poor accuracy. If any intermediate rounds produce an error rate higher than 50%, the weights are reverted back to their original uniform values, and the resampling procedure is repeated. So the initial splitting point can be selected randomly or based on the lowest entropy value. Let's say if we choose 0.35 as the initial splitting point, on the left of 0.35, all the points are classified as positive 1, and on the right of 0.35, all the points are classified as negative 1. So in this case, there will be 3 points are classified wrong, which are 0.8, 0.9, and 1. If we use another splitting point, let's say 0.75 as the initial splitting point. So on the left of 0.75, all the points are classified as negative 1, and on the right of 0.75, all points are classified as positive 1. Then in this case, there will be 3 points are classified wrong, which are 0.1, 0.2, and 0.3. So let's use this same example to see how it works. So for the training set, so the first round, the splitting point is 0.75. So in this case, on the left of 0.75, all the points are classified as negative 1. On the right of 0.75, all the points are classified as positive 1. And for the second round, the splitting point is 0.05, which means all the instances are classified as positive 1. And for the third round, the splitting point is 0.3. So on the left of 0.3, all the points are classified as positive 1, and on the right of 0.3, all the points are classified as negative 1. So let's use round 1 as an example to illustrate how AdaBoost is working. So compare round 1 to the original data. There are 3 points are mismatched, which are 0.1, 0.2, and 0.3, because the original data for 0.1, 0.2, 0.3 are classified as positive 1. But for boosting round 1, all the points are classified as negative 1. And we have a total 10 points, so the initial weight is assigned as 0.1 for each point. So according to the formula, the error rate here is 0.03 because we have a 3 mismatched and 7 matched condition. So based on this error rate, we can simply calculate the parameter alpha, which is shown below. Then the next step is to determine the weights for the next round, round 2. The calculation is based on the alpha value we just calculated, then normalize the number based on the number of correctly and incorrectly classified, which are 3 mismatched and 7 matched. So the predicted class is based on the majority vote. For example, at 0.1, majority round classified it as a positive 1. Then the predicted class is positive 1. And the alpha value for this point is simply the sum of all 3 rounds, which is 5.16. So the calculation for AdaBoost is a little complicated. Luckily, a lot of machine learning software can do this calculation for us. So in the next video, I'll show you how to do ADA boost by using one of the machine learning software. And that's it for this video. Thank you for watching. Hello everyone, this is Kelly. Welcome back. Let's continue our discussion about classification. So far we have discussed different classification models. Now the question is, which one is the best to choose? Which classifier performs better than the other? So in this video, we will discuss how to evaluate the performance of each classifier. Most commonly used measure is the confusion matrix. A confusion matrix summarizes the number of instances predicted correctly or incorrectly by a classification model. Few concepts illustrated here. True positive, which corresponds to the number of positive examples correctly predicted by the classification model. True negative, which corresponds to the number of negative examples correctly predicted by the classification model. Then false negative, which means the number of positive examples wrongly predicted as negative by the classification model. So we usually refer false negative as type 2 error. False positive, which means the number of negative examples wrongly predicted as positive by the classification model. We usually refer false positive as type 1 error. Accuracy is another widely used measure to compare the performance of classifiers. It's calculated based on accurate percent classification of the true positive and the true negative. But sometimes accuracy rate could be misleading when dealing with imbalanced dataset, meaning the class distribution is very skewed. For example, there are less than 1% of credit card transactions are fraudulent. Then a model that predicts every transaction as legitimate has an accuracy of more than 99%, even though it fails to detect any of the fraudulent activities. So in reality, we are facing many imbalanced classification problems: credit card fraud detection, intrusion detections, defect products, etc. So it's challenging to find these rare cases, like finding a needle in a haystack. And to solve the problem, we may consider to modify the distribution of training data. So the rare class is where represented in the training set. Commonly used techniques are undersampling and oversampling. Undersampling aims to balance the dataset by randomly eliminating some of the majority class examples. Oversampling aims to balance the dataset by randomly replicating some of the minority class examples. Another recent popular approach is called SMOT, Synthetic Minority Oversampling Technique. So this technique is very similar to oversampling method. It selects minority classes by utilizing k-nearest neighbor approach. By doing the sampling-based approach, your dataset between the two classes can be much balanced than before. There are also other metrics can be used to measure the performance of the classifiers. For example, use some alternative measures. Samples are listed here, so the counts in a confusion matrix can also be expressed in terms of percentages. Recall and precision are two widely used metrics employed in an application where successful detection of one of the classes is considered more significant than detection of the other classes. So precision means it determines the fraction of records that actually turns out to be positive in the group the classifier has predicted as a positive class. So the higher the precision is, the lower the number of false positive error predicted by the classifier. And recall measures the fraction of positive examples correctly predicted by the classifier. So the classifier with a large recall have very low positive examples misclassified as the negative class. F1 measure is just the harmonic mean between recall and precision. A high value of F measure ensures that both precision and recall are reasonably high. So now let's have a recap what we have learned. Here is a simple quiz. Which box indicates the false negative? Is it A, B, C, or D? So the answer is B. False negative is our prediction is negative or no for a positive or yes example. Sometimes we use ROC curve, receiver operating characteristic, to measure the performance of classifier. The ROC curve is a graphical approach for displaying the trade-off between true positive rate and the false positive rate of a classifier. In a ROC curve, the true positive rate is plotted along the y-axis, and the false positive rate is plotted on the x-axis. So each point along the curve corresponds to one of the models induced by the classifier. So a good classification model should be located as close as possible to the upper left corner of this diagram. So the blue diagram line represents a model makes a random guess. And we have equal probability to get a true positive rate and false positive rate. It means if the model predicts the result under the blue line, which means the model performs worse than if you do a random guess. So in this case, you just random guess rather than use the model. So the ideal situation will be true positive rate equals 1 and false positive rate equals 0. There are some other critical points along the ROC curve that have well-known interpretation. So the true positive rate equals 1 and the false positive equals 1. So the model predicts every instance to be a positive classes. When true positive rate equals 0, and false positive rate equals 0, and the model predicts every instance to be a negative class. So a ROC curve is also useful for comparing the relative performance among different classifiers. So in this case, Model 1 performs better than Model 2 when false positive rate is less than, let's say this is a 0.36. But Model 2 performs better than Model 1 when false positive rate is greater than 0.36. Additionally, the area under the ROC curve A, which is also known as AOC, provides another approach for evaluating which model is better on average. If the model is perfect, so the area under the ROC curve is 1. If the model simply performs random guessing, the AOC will be 0.5. So a model performs better than the other, so this model would have a larger area under the ROC curve. So classification has always been a major research topic in the area of neural networks, statistical learning, and machine learning, etc. Recent years, it's also widely used in speech recognition, handwritten character identification, image classifications. I hope you got a general understanding about what classification method is, and right now you are able to use it in your future work. And in the next video, we will have a hands-on exercise to learn how to perform classification tasks. And thank you for watching. Hello everyone, this is Kelly. Welcome back. For this video, we will continue our conversation about classification. From previous videos, you have learned the concept of classification, gain an understanding of different classifiers, and know how they work. You also learned how to evaluate the performance of different classification models. Now it's time for us to learn how to perform classification tasks. We will use Veka, a widely used machine learning software. It is publicly available and it's for free to download. You can go to this website as shown on the slide. Then choose Download and find the appropriate version of the software based on the type of your computer. For MacBook users, once you download the software, you will need to go to System Preferences. Then, under Security and Privacy, on the bottom of the screen, you will see a message like this on the slide. You can click on Open Anyway. Then you can run Weka on your computer. Once you open Weka, a small window like this will pop up. You will mainly use two applications, Explorer and Experimenter, and I will show you some examples. If you click on Explorer, a window like this will pop up, and if you click on Experimenter, a window like this will pop up. So now let's see how to perform some classification tasks. In this case, I use the dataset from the UCI Machine Learning repository. It's a very popular machine learning database. You can find a variety of datasets to exercise your classification skills. So in this case, the dataset I chose represents 1984 US congressional voting records. The classification of the dataset is to predict the votes for each of the US House of Representatives congressmen, either Republican or Democrat. So there are 16 attributes, 435 instances. So the dependent variable Y is the political parties, either Republican or Democrat. There are 9 independent variables, which are the attributes are listed here. So let's see how we can use Weka to perform classification tasks. So first, let's bring out Weka. Once you open Weka, a little window like this will pop up. So we can click on Explorer first. A window like this will pop up, and let's enlarge it. So first thing, we need to import the data set. So click on Open File, then go to your data folder and choose the file type. In this case, I have a CSV file. And click on Open. So first, we have to check the type, your data type in this data set. So one way to check is click on the name of your attributes listed here. As you can see, most of them are nominals. Another way to check the data type is under the Edit. Here you can have a holistic view of your each attributes. In this case, we can see that everything is shown as a nominal. Sometimes when you have a data set, the data type is numeric or other type other than the nominal. This requires you to perform to convert the data type to nominal. In this case, what you need to do is go to under Filter, click on Choose, open these filters, then under Unsupervised, and choose this attribute. So the function we want to use is to, for example, convert the numeric to nominal, right? Then you apply. This will convert the data type to nominal. All right, since this data set, all the attributes are in nominal functions, so we don't have to do this step. But just in case in the future you have a different data set, you can consider this pre-processing step. So once we have the data imported, we can go to Classifier tab here. So under Classifier here, we can choose the algorithm that you want to use. So there are different algorithms available here. So in this case, let's choose decision trees. In Weka, decision tree is called J48. So just and once you put your mouse over J48, there's an explanation will pop up, so you can read it. So we choose J48. In this case, we want to split the data set. We want 80% as my training set and 20% as my testing set. All right. So my prediction number here So you have to tell Vecca what is your Y, right? So right now I choose a class name. Then you click on Start. So now, because this is a small data set, this is Vecca runs really fast. But if you have a larger data set, it might take a little longer time to run. So in this case, we run a decision tree here, and the results are listed here. And number of leaves the tree is showing as 6, the size of the tree is 11, and the accuracy rate of this classifier is 94%, which is pretty high. And you can see here all the different measures are, the results are listed here, and including the confusion matrix. And for decision trees, you can also see the tree. If you right click on here, choose visualize tree, you can see this is your decision tree. All right. You can also choose a different classification model. Let's say in this case, we want to do ADA boost. It's under meta. I choose ADA boost. And I want to keep the rest the same. So I want to start. So in this case, ADA boost have relatively higher the accuracy rate, which is 96%. For decision tree, we had about 94%. All right. So now we're going to try to use a different approach for the classification models. We're going to go get out here. So now we're going to try experimenter in this case. When you click on experimenter, a window like this will pop up. So let's enlarge it. So first, you want to click on a new because we want to generate a new workbook, right? So then here you want to define your destination for your results. After the model runs, generate a file of your model performance. So that's the results file that you can generate it. So you can either choose ARFF file or CSV or different database. So in this case, I want a CSV file. So now here you can define a directory. Where do you want to save this file? All right. So now here, the next selection is experiment type. In this case, I chose a tenfold cross-validation. That means the data set is divided randomly into 10 equal size parts to generate each pair. So we keep one of the 10 parts out as the validation set and combine the remaining 9 parts to form the training set. So we do this 10 times, and each time leaving out one of the 10 parts so we can get 10 pairs. So then here the iteration control means I want to do, you can choose 3 times or 5 times or 10 times how many times you want to do the cross-validation. So in this case, I want to do 3 times just to save the time. So now I want to add a data set. So to add a data set, simply click on Add New. Then select the appropriate data set in your folder. In this case, I have a CSV file, and click on that. Click on Open. So now the next step is to select the algorithms that I want to use. So click on Add New. Click on Choose. In this case, I want to select decision tree, which is J48. Then click on OK. Then we can add another algorithm at the same time, which we're going to choose Add Random Forest. Click on OK. Then we're going to add another one maybe. In this case, I want to add ADA boost. So now the setup is done. So we're going to go under the tab Run to start. It's very fast. So once you're done running the model, then we go under Analysis. You click on Experiment. This will bring the results from previously run experiment to here. So now we want to use paired t-test, which is to compare the similarity of the two classifiers to see whether they are significantly different from each other or not. Then in this case, if we want to compare the field, you can compare the percentage corrected, means accuracy percentage, or as we learned, we can also compare the area under the rock curve. Then the next step is the paired t-test is set at 5% significance two-tailed test. All right, so after we set the parameters, we're gonna run the action right here, perform tests. So here is the results. So in this case, and in VECA, V means significantly better, and the star here shows significant worse. So in this case, for the data set Congress for random forest, which is number 2, and AdaBoost, which is number 3, they are significantly better than the decision tree. I think that's it. That's all for this video. Thank you for watching.